Okay, so we're going to go with the order that I've shown the videos. So the order is first Juxi Leitner, and then Jeanette Bock. She said she would join at some point after now. And then Professor Karen Goldberg, and then Professor Peter Fox. So the first question for Juxi Leitner is from Andreas. Another surname. It says, if you combine reactive grasping with traditional visual grasp planning like DexNet, GrassNet, GPD, how well do you think this would work? What do you think would be the remaining failures?
That's a good question. So I think that's sort of what we were aiming to get to, right? And I think it's the same in Ken's lab as well. The reactive part, I think the point there is to be fast, right? So whatever visual grasp planner is providing you inputs, as long as this one is fast, you can deal with changing environments. That said, obviously, that's not going to solve everything, right? So it solves things that are moving, or if the pile of objects that you're picking from, clutter, for example, is changing while you're actually going towards it, then that makes a huge difference. And we've actually have a paper on that as well, where you can actually use the information from the trajectory when you get towards the object and integrate that over time into your visual grasp planner. You actually get better success overall. But I think it doesn't solve everything. And I think it was also in Dieter's talk, and I think also Ken's talk about the sequential failures. So there's certain things where purely reactive by itself is not going to be good enough, right? So you will need to extend it with either memory aspect of things, or something where you can actually have some, let's call it reasoning about the scene, where you can move things out of the way, or where you need to adapt to other things that are not purely reactive. So I think it's an important critical aspect. For me personally, I think it's a very important aspect, but it's sort of, if you think about it, sort of the low level reflective behavior, and you want something on top that makes some higher level decision. That's how I at least feel about that.
Do we want to?
Sorry.
Do we want to run this where you go by person for 5 minutes with multiple questions, or should we have maybe a more general discussion, or is it going to come afterwards?
I'll just do some questions that people posted on the chat first, and then we do more of a general discussion. But if any of the questions that people write triggers a more general discussion, jump in and comment on it by all means.
Oh, we can't hear Ken.
Yeah, I forgot to make him co-host.
Oh, good. Okay. No, just because I couldn't unmute there. Actually, it's up to you, Zhao. I mean, I think we could have a little discussion on this.
It might be fun.
Yeah. Okay. I do think the reactive is really interesting. I mean, we sort of framed it in this question of non-Markovian, right? Where we would try to remember errors over time. And I do think there's value to that. And there's many different ways of approaching it, as Juxi said. I mean, one is, this idea of continuous learning, right? Where you could just be retraining a reactive model over time. And especially where, mistakes are very valuable there, because they help you, you can actually correct your models. So that's useful to have negative examples, right? Counterexamples and adversarial cases. But we were also looking at very specifically just the process where the system would, let's say, fail to grasp something, and then it would essentially pull the hand back. It would have failed to grasp it. And then it would basically be looking at exactly the same heap as before, and then it would keep doing that over and over again. And that's sort of a loop that we really want to avoid. So, I think that it is important to try and have some local history also. And I'm just curious about how others are thinking about that.
No, I totally agree on that. That we've seen cases where actually just trying the same thing again and again, because a failure often causes the object to move slightly or things like that, can actually work. But I also agree that these techniques like GraspMet or so, right, that the important part is that they can generate a variety of different ways of grasping objects, right? And then you can actually try different ones. But we need clearly to go beyond that, where we're trying different viewpoints, maybe slightly pushing an object. And I brought that up in my talk, for example, when we did this DEX pilot work, where you see humans doing actually very complicated grasping or object manipulation tasks. And it's incredible when you see this, right? I mean, for us, this is all simple, but from a robotics perspective, it seems like humans are able to, they try something, and then if it doesn't work, we have a really strong capability to kind of have a sense of why it didn't work. And then we say, okay, that was close enough. Let me just try it again, because it was just kind of maybe a control failure or something like that. And then you try that 2-3 times. And if it doesn't work, then suddenly we can come up with a totally different strategy, right? Where we say, oh, let me try it from a totally different perspective, or move the object first and things like that. And I think that is something that Ken also mentioned, like this lifelong learning. We need to have really smart kind of exploration strategies, right? You don't want to just randomly try different things, but you want to do that in a highly informed way. And that is the tricky piece, how to get a system that has that kind of understanding that supports such an informed exploration.
For me, one of the critical aspects for that is simulation, though, right? I mean, as you say, like humans are quick to adapt if they like quick to start moving, and then maybe sort of rethink approaches even while they do it, right? So, like for example, in the example that you brought with like picking up something in I think it was the cereal box or something in like, or the cup between the cereal box. Mm-hmm. The humans probably start reaching, and then sort of like, oh wait, hold on, this is actually not going to work out the right way. So I'm like, either move things out of the way or adapt on the fly. And I think that's something I fully agree. We haven't really done much yet as a community, right? Like I think that's sort of really the transition from grasping to manipulation and like higher complex tasks. And for me, I think that's something where simulation can play a more important role than it has done so far. And sort of like, you know, sort of forward proposing solutions and sort of in your mind, or in this case in simulation, play it through and see what would happen, and basically feed that back into your either your reactive controller or your visual feedback controller that then can make these decisions.
Yeah.
Although I'm interested, Jixi, I'm surprised a little bit that you said simulation here, because I'm just looking at your paper on, I think it's a maybe choral paper, but you have a paper on learning from real, right? Which is really interesting. This is for fabrics and other materials, right?
Yep.
But you know, I was struck by that because we've been having a big discussion in my lab about that idea of you know that in certain contexts, simulation is so difficult that actually there is an interesting possibility of learning just from real examples, especially if they could be self-supervised. And I think that getting back to what Dieter's saying about almost diagnosis of failure is very interesting, because I think you're absolutely right. We haven't modeled that at all, really, and I think that humans do that. You know, children, they'll understand that why that slipped out of my hand, and they'll figure it out. You know, those are process. So I think that's really interesting, is where you can really sit down. Let's say there's a part that you often are dropping, and really sit down and really try to have the robot essentially either in real or sim, but just systematically go through different options and really try and figure out what's failing, what works, why, hopefully. That's really interesting and new terrain as far as I know.
And there seem to be different ways of using simulation, right? One would be, let's say, the typical deep learning in simulation, but I think Yuxi meant it a bit more in the context of simulation just as your internal physics model to do predictions of the world, right? Kind of in an online fashion where you say, here's my scene, I kind of have my internal physics model, be it now an accurate simulator or something learned, and I'm using that to try out different alternatives and predict which one is likely to succeed or not.
Maybe
yeah, no,
online
exactly
finding,
right.
I was thinking online you can find whether there's a discrepancy between what you predict is going to happen on simulator and what actually happened in reality. And this is where you have to react. This is what you have to react to, right? This is the unexpected.
Yeah, exactly. So that's exactly right. I think that's the unexpected things that we, like that we can't really deal with right now. And yes, I think I've always sort of tried to do as much learning as possible from the real world. And we had some people doing sim to real transfer here. And I think for me, the biggest question is where's the right use case for a simulator? And I'm not really sure it's really just like the tactile, slip forces or something like this. I think we're having a lot of trouble actually simulating that. So we sort of tried that very early on and really didn't help us much in progressing the state forward. But I think, as Joao also mentioned right now, I think that's sort of like the reasoning and sort of the unexpectedness, that's something where simulation, I think, can make a huge difference. And as Ken said, I don't think that's been really explored too much yet, but I think it's a great opportunity for all the researchers out there. I think that's a really important avenue to go down that really will push that forward really towards manipulation and not just, top-down grasping, which is, what we've done for a long time.
Yeah, it just strikes me that if you're using a simulator to train your system, then if the system fails in reality, then by definition, it's a case where you have a gap between sim and reality, right? Because the sim predicted that was going to work. That's why you actually did that action. But if it fails in reality, that's interesting. It also sort of triggers this curiosity or something, right? Where you have this gap, and now it's something to learn from. And to actually, I mean, in some ways, it's actually interesting because if you buy into that, the value of that for learning, then you actually want to fail. Right?
You just don't want to fail all the time on the same problem, right? So I guess that's the other aspect of curiosity that I think Dieter also mentioned before. Like, you don't want to pick up the same object over and over again, right? You want to have a possibility of different alternative strategies or whatever you want to call it that you actually can explore. Exactly. And I think that's really, I think my PhD supervisor was super keen on artificial curiosity, and I think there's a lot of value to it. I'm not sure we have really scratched the surface of what it can actually do for us in robotics yet. And I think that, like, for me, like in that simulation and sort of this forward rollout or dealing with this sort of unexpected things that happened, whether as in forward rollout or as in like determining what sort of went wrong. I think that's a really interesting aspect where we can apply some of these ideas about curiosity or whatever you want to call it. People have used different names for it, but
And that seems something that, of course, happens to us humans all the time too, right? We have our, let's say, it's not sim to real in the sense of, let's say, the deep offline learning, but in the real-time setting that we have our internal simulation model based on which we say, well, that grasp should work. And then for some reason, sometimes it doesn't work, right? So somehow our internal simulator was wrong too, and then we just have to react to that.
Mm-hmm.
Some people say that's the case for humans, exactly like that. We function in a sort of a Bayesian way, right? So we would have some expectation of what's going to happen. And when it doesn't, we have this reaction of like, what happened here? We readjust our models to cope with what we're seeing.
Yeah.
But this just another thing when we about these reflexes that I was thinking. So we're talking about reflexes in this sense of like when you're going for something and something happens on the way. But a very common mode of failure is slippage, right? And that one is a bit more difficult to react against, right? Because that one you're often not fast enough to react to that.
I would say if you have touch sensors or so, then clearly people have shown that you can become pretty reactive to these, right? Where you detect, there was a lot of work on slip detection and things like that. So I think that's where touch can help quite a bit. And it seems like with any of these components, right? Like touch sensing for slip detection or better sampling of grasp poses and things like that. we can improve overall success rate, right? And then the question is, what can we wrap around these to come up with a truly robust system?
Mm-hmm.
Absolutely. Like we were watching your video, Professor Fox, and you spoke about a lot about like the wrong pose. Sometimes the pose of the object that you detect is wrong, or the calibration is. So there's an inconsistency between what you see and what you feel, right? Is that because we're not using tactile sensing enough? Because I can see tactile sensing as something that both improves the detection of the pose and also fixes the calibration between the eyes, the cameras, and the gripper.
Yeah, I mentioned that. So when I talked about, let's say, this more model-based approach, right, versus the purely learning-based approach, where you're going, let's say, if you have an object model and you want to use it for grasping, which means you first detect its pose and then do your grasp generation, everything based on that object model and the pose that you estimate. And there is just this inherent brittleness to that system, because you're kind of compressing all the information that you're getting from your camera to a 6D pose and a model. And if in practice, the model shape isn't exactly right, or the camera calibration isn't exactly right, there's always something that can go wrong, and these things then add up. And I agree that if you have touch sensing, then you can kind of make it less brittle, right? You can come up with some techniques that kind of make you succeed even when the pose estimate is more wrong than it would usually be able to succeed on. And that's one way for coping with some of these pose errors, right? And then you can do things, as you mentioned also, you can maybe use the interaction itself to refine your pose estimate, or you can come up with more robust behaviors using touch sensing. So I think that's a good way for improving this kind of line of work, right? That is more pose-based versus the work that goes more directly from, let's say, point cloud or camera data.
Mm-hmm. I just want to. I do feel like I want to be a little contrarian there on the tactile. Partly, I think, because I started working in tactile as an undergrad, and sort of it's struggled through working with tactile sensors for many years. And I think it's really important to understand how there are limitations, that we just don't have good tactile sensors. I know there's been a lot of improvement, gel sight and the kind of tools that Alberto Rodriguez have been developing recently are really interesting. But I do feel like, there is this sort of philosophy that you get more sensing, but it's also more source of error and noise. And so, and it's very hard to figure out what to do with the tactile data. I agree with that. You could detect incipient slip. It's interesting that that could be helpful in certain ways, but it's surprising to me. I mean, I just would conjecture that it may not be, that tactile may not be really the answer. And especially in real practical uses, like industrial uses, where you really want to have a system that's running over a long period of time, day in, day out, sorting packages or filling orders. Tactile tends to degrade, deteriorate over time. And that's why I just don't know if it's going to end up being a robust source. Happy to be argued about out of that, though.
No, I think sorry, I jump ahead there. So I think the saying that I've heard a lot is tactile sensors are either expensive or don't work very long, or in the worst case both, right? So I think that's still a very true statement. I think the other aspect though is, and I think Ken, you also hinted at that, it works in a quite different space to vision, right, or some other sensing. So we haven't really figured out how to bridge that yet. I mean, yes, we can do slip detection, but like how to merge these sensors together to actually do something, something like we do with our hands, where, I slap my hand on the table and sort of slide it across until I touch what I want to actually pick up, right? I think we don't really know how to do that yet. So I'm also skeptical of tactile sensors. I can see it as sort of a backstop or sort of something that's a fallback method. And especially sort of for our industrial applications, we've tried it, and there's really not a lot of useful cases that we've seen where it's going to give us a significant difference in performance, given also the price that is usually very expensive for it.
Yeah, I agree. And it's interesting that you say that also, Ken, with respect to kind of that it seems to make things more brittle. So when we started working with tech, we've been using the biotechs for quite a bit. And I also thought, come on, with textile, it must be easier to pick up a cup than without tactile, right? But it turns out it's so complex to use the sensor data that in the end, the picking up of objects seems sometimes more brittle with tactile than without. But my hope is actually that that is still just the case because we're not that great of knowing how to best use tactile information. So my feeling is that tactile is not going to make problems go away, but it might make things a bit more robust, right? So as we've seen, for example, again, in my talk, there are some videos of this DEX pilot work where they're controlling an Allegro hand, but a human is controlling the Allegro hand. And there's zero tactile feedback, and they can do incredible things that you would never be able to do right now in any autonomous system, right? So again, humans are ingenious in coming up with solutions to these problems using other sensors than tactile, for example.
And the other example of that is Da Vinci and all the work that's done there where there's no tactile.
Mm-hmm.
And
Because I guess, sorry.
can I comment on this topic? So I think that I agree with the opinion that the tactile has a limitation, but I think that it would be also interesting to consider the proximity sensor.
Mm-hmm.
And I think that by using proximity sensor, we can sense the object before contacting it. So I think that we had better take into account such another sensing modalities.
And Suki, what kind of proximity sensor are you thinking of? Optical, or what would you?
And in my laboratory, an assistant professor is working on the proximity sensor. It is based on the LED.
Mm-hmm.
So
And a colleague of mine, George Smith, most recently, I think it's infrared in the fingertip sensors, but he did very early on this E-field sensing where he looked at the electric field and disturbances of the electric field that's induced by objects when it gets close to these. And he was able to use that to do some really nice object handover and pick up tasks and stuff like that. So I agree that the pre-touch kind of sensing, right, can help with this transition from more visual-based reasoning to like real touch sensing.
I was just going to say that this thing of looking at people teleoperating or doing surgery, they're not explicitly doing they cannot sense contact, but it like they look at how the things deform, mm-hmm. And we're very good at seeing how things deform. We know how much force, you know how hard you're pressing, you know what I mean? So you're not explicitly sensing force, but you do need that force information. That's very difficult to get from train an algorithm. It's difficult.
Yeah, essentially we need to reason about contacts, right? Especially also soft contacts and things like that. Yeah. There's a comment in the chat by Neil Doshi.
Oh, yes. Yes, that's another difficulty of having, I think another difficulty is you might need to explicitly reason about the hybrid modes, stick versus slip, once you detect slippage. True,
yeah.
True.
All of these are very hard, yeah.
No, yeah, let me unmute you then.
Hi.
Go ahead,
Sorry.
Lou.
Can you guys hear me?
Yeah.
So you mentioned Alberto, and I've been working on a postdoc with Alberto. I've been working with Alberto for a while, and we're thinking about this. So I don't mean to speak for him, but just my 2 cents is using sensing becomes hard, especially when you're manipulating about external contacts. So if you're doing something besides grasping, like some kind of non-prehensile manipulation, like a pivot or a push or something where you have an environmental contact to reason about, then you need to use your models in order to predict what's happening at that contact. So recovering from slip there, maybe you can't just rely on sensing. And the other thing is, if you have multiple contacts and they all may stick or slip, then your controller, the complexity of your controller becomes it's much higher. And then the last bit is, if you do have good model information, you can try to find policies. And I think Yifan has some recent work even on this that sort of keep you in the middle of your friction cones as much as possible. And so they're really robust to slipping, because in a lot of cases, that's a behavior you can avoid. Or if you, sometimes you do want to slip, but if you want to avoid it, this is a good way to do it. But of course, it requires that your models are good. Just some thoughts.
No, yeah, and if you're only using tactile sensing, not even obvious to detect when you're sleeping. Like you can think incipient sleep is vibrations, right? But I mean the robot vibrates, so you might feel those vibrations. Or maybe if you're sliding let's say you're sliding a credit card on the table, it's difficult just based on tactile sensing alone to find out if it's your finger sliding on the credit card or is the credit card and the finger sliding on the table.
Yes.
Is that so? Whereas with vision, this is trivial.
You mean with vision, it's trivial to detect the slip? Or
To detect whether it's your credit card that's, let's say you're sliding a credit card on the table, if it's the credit card sliding on the table or the finger sliding on the credit card.
okay.
Whereas with tactile sensing, this would be just vibrations.
Mhm.
You can sleep effect.
It's not quite trivial with vision, still, unfortunately. That would assume
Maybe
that
because the credit card is small and you're occluding it, right? So you have this.
But I agree, principally, yeah, you're right.
It would be maybe interesting to get a bit more from Ken out of this one. You know, as he said, you worked on tactile a long time ago. For me in vision, right, we've vision sensing gives you a lot of information, right? Every pixel has color information, and you can use that for a lot of different tasks, right? From object detection to tracking and so forth, right? And for all of them, we might have slightly different processes, but I think we're getting really good at having processes for a lot of these tasks based on the data that comes out of the sensor. From a tactile point of view, first of all, I think there's still like different tactile sensors provide you different information. So how do we deal with that, and sort of how has that changed over time? And how do you feel about like sort of the processes that lead us to understanding out of this data? Do we now have stick, slip, other aspects that come out of the tactile sensor? Have we made progress on those processes, or is this sort of like the biggest hurdle for us? We haven't figured out how to use them yet.
Well, I think one thing is, the big challenge with vision is occlusion. Once you're doing the grasp, right? You're actually, it's very difficult to see the contacts at that point. I do like the idea of some proximity sensing. I think that's interesting, Kensuke, because I in particular, here's one scenario that I've been thinking about a lot lately is suction cup, which is single point grasping, right? So that would really benefit from having a proximity sensor, because you can imagine projecting a little ring onto through the suction cup and a little camera in there. And so as you're coming close, you can actually, very quickly servo so that you get a nice, circular projection, which would indicate that you're orthogonal to the surface normal, you're orthogonal to the surface. And that could be very useful. Now, the challenge is, just some engineering about building that into a suction cup. That would be, but I believe that would be doable. I haven't seen anyone do it. But of course, the other thing we get a source from is actually the suction airflow itself is really interesting, right? So you can, as you're lifting, you get a signal from that, and you can actually check if you're losing air pressure. That's an indication. It's like slip, a little different, but that's an indication that you would have to readjust your grasp or press harder. So there's a lot of interesting nuances to that. And of course, people are looking at in-hand cameras or various kinds of since cameras are reducing in cost and size. The other thing that we've been really interested in, I know many of you are as well, is depth sensing. that seems to be very helpful because to my mind, depth is really exactly the right thing because it gives you geometry that you can, is really what you want for grasping. At least in, for rigid objects. The challenge is depth sensing, is very prone to noise and anything transparent or reflective is really, problematic.
Yeah, that's where it also gets then interesting from, let's say, the computer vision community, for example, right, where they're looking at how can you do object shape completion and things like that, right? And we've also recently done some work. If you train it on transparent objects, then you can start actually coming up with a 3D rough shape model of the object, even though you can't explicitly visually really see that, right? And
yeah, no, that's really interesting. You've done some work, and I think Jeanette has some results.
Yeah, that's true. Yeah,
and really interesting. No, I agree. That's very interesting. Can you sort of learn to infer the geometry from partial information based on examples? Really like that idea.
No, the question is, do you want to go from that image to 3D geometry and then based on the 3D geometry do your grasp selection or planning, or do you just want to go directly to the grasp planning and selection, right? And have your geometry maybe somewhere implicitly in your model, right? And it's still not clear to me what the better approach there is.
Well, here's my answer to that, Dieter. I want the image. I want to go directly from the image to an action, right? But I want that image to be coherent. In other words, if the image contains a lot of noise or false surfaces, then that's not a fair input to my trained system, right? Then I can't really, I don't think any function approximator will be able to take a noisy, pathological image and then be able to work with that.
Yes, but the question is, could you, with that same image, could you go to a 3D shape model rather than that? And if you can do that, then maybe you could also go to directly, let's say, to the grasp planning. But I'm not trying to advocate here one over the other. It's still, I think, a very open question, right? Whether you ever want to go through an explicit representation of shape or whether it's just mostly encoded in how you behave and reason about the world.
Right. And the nice thing is you can actually encode a fair amount of the signal processing, the noise reduction into the same neural network that's learning the action model. So that's what's so interesting is that the network seems to have so much capacity to actually combine both of those.
Mm-hmm. So, yeah, it's like for example, with the GraspNet stuff that we did, right, where you sample 60 grasp poses from point clouds directly. And then you could ask, like, because the network obviously comes up with good ideas for grasping these objects that's consistent with the geometry. So obviously that network internally has some reasoning about geometry, right? It's just not explicitly done so. And you can then use the same approaches for placing objects and doing things like that. So we'll have to see how far you can get with that.
Yeah, definitely.
I guess for me, the interesting aspect would be, how do you, given that, for example, you have different sensing capabilities, and whether that is tactile or proximity or whatever it is, how do you then make a choice on sort of a higher level, which ones of your sensors you can trust? And that sort of falls back a bit to what Ken said. Like at some point you might see something that you haven't trained in your system, or there's too much noise on that specific sensor. So how do you make that decision? And the nice thing about an explicit model is that, yes, you might be able to reason about that one, but is there something that we can do with this inherent or implicit modeling that's going on in the neural network that we can ask about a confidence value or an uncertainty of the network itself, so we can still use that information to inform the higher level decision making that says, well, sensor A doesn't seem to be working right now, so let's go to sensor B.
Well, you would hope ultimately that the network just figures out how to combine them, right? Let's say early fusion or so, and that it can do a job that's at least as good as what we would do, let's say, by taking the output of the individual channels and then somehow, even if you do Bayesian reasoning on them, right, might not be as good as combining them in a fully differentiable end-to-end way. Again, I don't know, and I think not many people know.
Going back to the idea of failures, I think it's interesting that we, it's interesting because we're all writing ICRO papers, right? I'm guessing right now, and so there's always this thing about fear of failure on the part of students. They're really shy away from it, and they're like, I keep coming back. The failures are the fun part. That's what's interesting. Dive into the failures because that's where you're learning something. And I think that we have to show that the network has to see failures, or the system, if we're going to learn something. And that's why, Yuxi's the paper you have on EGAD is a really nice example of this. And where they systematically generate this really rich scope of objects. I found that to be really interesting and a big contribution. I mean, we used it actually in a paper. Like literally, we were about to submit, and we ran it through a number of your objects, and it was super helpful because it really helped us say, okay, here's ways that this system would fail. And I think we need those kind of things, those failure benchmarks. Just as Vision does this all the time, right? They're very good about identifying failure modes. I mean, Dieter, I don't know if you're really at the borderline between the two. So what is your perspective on that, from how Vision does this versus robotics treating failure?
For whom is that a question?
Well, I'm curious about, I mean, we're here to talk about failure and grasping, but I'm actually sort of just occurs to me that, in Vision, there's such a, there's an emphasis on mining, failures and negative examples, and crafting, adversarial images. What do you think about that in terms of, is that happening in robotics? Should it happen more?
Well, I think it's not happening enough for sure, right? In general, right? Like the whole benchmarking notion, right? And in that context, also in benchmarking, figuring out what doesn't work and focusing on failures and things like that. On the other hand, I must say, even in Vision, often with the data sets, right? The evaluation is some accuracy numbers or something like that, right? And often I think there is actually a lack of a real understanding of why these different techniques fail, right? It's often boiled down to a table where you show that you have very good numbers, hopefully better than the others. And there's not so much reflection on, could that network, for example, could that even do the kind of reasoning that you would want it to do, right? We've seen this in the context when we did this kind of, let's say, model-based manipulation, where, of course, 60 object pose estimation is a really important aspect of that, right? Like how accurately you can estimate the pose of these objects. And there are all the benchmarks out there, and they focus on things like average centimeter, how much you're deviating from the correct pose on the surface of the object, or how much you are within a fraction of the size of the object and things like that. But these numbers in the end, they actually don't tell you anything how useful that will be for manipulation, right? So I think what we will have to come up with is measures that don't only look at, let's say, accuracy of a 60 pose, but how much will that translate into a grasping failure or something like that, right? I think that would also be an interesting aspect, how we can look at these things more from a robotics perspective, like from the end task, right? How much they support that. But I agree overall,
I think
more benchmarking and things like that.
Yeah, I think Vision is maybe a step ahead there with there's quite a lot of work on, or at least a significant amount of work going on into like adversarial images and like how to fool neural networks and so forth. I think that's a bit lacking, but I think as Dieter said, I think that sort of just seems a bit of a general lacking in how to test robotic system and benchmark robotic systems. For subtasks and subsystems, we have pretty good measures, but it's not always clear how to translate into larger problems or into errors of a whole system. And I think that's sort of something, especially when you try to transition these things into industry, becomes a really important part of it, like which part of your system is actually working. And in the end, if you go to a customer, they don't particularly care about like, which black box magic is underneath the hood and how accurate that is, but like, what's the overall performance of your robotic system? If it's mean picks per hour or throughput or cost per pick or whatever it is, but in the end, that sort of end to end is what drives them. And we need to, I think as a community, we need to find a better way of translating that back into where is actually the improvements that are relevant to be made. Yes, I can push maybe the 60 pose estimation further down, but if my accuracy with like the manipulator is not good enough, what's the point of being sub-millimeter accurate in your 60 pose?
So if I understand correctly, you kind of agree. You're talking about failures in the sense of like they're useful for benchmarking, but I'm wondering if they're useful on a more sort of, so this is the final product. Are they useful? Would they be useful, particularly in learning strategies that they can somehow be included into the learning, rather than just at the end to benchmark to see, okay, this fails less than something else, but to be part of the same with people, right? People say there's a saying that we learn from our mistakes, right?
Yeah. I mean, absolutely.
No, I think we all agree.
We mentioned that before already, this notion of, I think, that it's really important if you want to have a system that just operates continuously, right? And just doesn't, whenever there's a failure, immediately stops and has no idea what to do, is you need to be able to kind of make sense of the failures that you're making, right? You need to understand what might have gone wrong and then be informed to try alternative strategies to overcome that failure case. And then all this experience that you're collecting, you have to continuously take into account in order to improve your system and learn from those failures. I think that's a crucial thing we need to add to these systems.
Yeah, this was sort of what Ken Goldberg had in his presentation. So when you keep on failing with the suction cup, kind of you take a memory of these failures and change the approach. We had the similar thing yesterday, similar session yesterday. And the first question that came up was like people couldn't agree on what a failure in grasping is. So is failure in grasping, is it the failure to complete a task? Is it getting to a grasp that is not stable, but somehow the task gets done? Or is it something that is repeatable and predictable? So this is success, that being a success, something that you can predict how it's going to behave. You have any thoughts on that?
I'm smiling a little bit, and thank you for getting to the second question, Chow. It's funny because we've been talking for 45 minutes on the first question, so.
I guess this is, I prefer this type of workshop rather
no,
than.
it's fun. It's fun. I'm enjoying it thoroughly. I would say, it makes me smile a bit because, to my mind, there is, and I think it's a great question because my first answer is no. It's obvious you fail when you drop the object, right? I mean, that's unambiguous, but you're right. There could be nuances to that. When parenthetically, I always like to say, I'm so glad I work in grasping rather than driving. Because you fail in grasping, you just drop it and try again. Driving, you don't usually get that chance if you're, go off a cliff or something. So, and by the way, I do think this is why grasping is actually, I'm a big critic, like Rod Books or a skeptic about self-driving cars, and I don't want to get sidetracked into that category of failures, but I do think I've been skeptical about when that's going to be adopted. And on the other hand, I do think I'm much more optimistic about manipulation and grasping being deployed, robotic grasping being deployed more widely, and it's because of its failure, because it is somewhat fault tolerant, right? It's not terrible to have a certain amount of failure rate. In setting, that's completely acceptable. So you don't have to get out to that 99.9 level in order to be useful. But coming back to your question, I'm curious how others feel. I'm just trying to think about what would be a failure, more nuanced measure of failure.
one of the speakers yesterday, the example he gave was that, say you're trying to put something on a box and you grab it, and then as you're moving it, it just slips out, but happens to fall into the box that you were planning to put it on. Is that a success?
So I guess for me, it comes back to the metrics that you want, right? So and I think that's the other thing that maybe as a community we haven't really fully explored, or at least explored options of defining that a bit better. And I know Jeff's wrote a paper. Jeff was one of Ken's postdocs, I think, students, about a specific GRAS metric, and I think I've been on another paper that explores a different GRAS metric. So I think as a community, we're not really sure what to define as a failure or how we define a success rate. The interesting thing is if you go into industry, all of that in the end sort of becomes really void, because in the end for them, they have a specific metric, as I said before, like mean picks per hour or throughput, and that's really what matters to them. And if you take 3-4 trials to pick it up, that's fine, but in the end it will drop this MPPH number. So I guess for me, there's different metrics at different levels. So an end-to-end task metric is probably important to have, but there's also a question of how to translate that last metric into like metrics that are helpful for you to progress the system. For example, internally here at Lyra, we use quite a different metric to understand whether we are making improvements on our robotic systems, because we don't want to run like 24-hour long end-to-end tests on the whole system after every code commit or after every piece of hardware change, right? So there's other ways that we sort of use as sort of placeholder or intermediate metrics that help us access or see what sort of success we've made with a change, or ideally success. Sometimes it's not really a success, right? So, but I think that's sort of a case where failures are, that the question is more on how to define the failure and the metric around it, not so much the value of it, right? So I think failures at all these levels have different inputs and provide you something valuable, whether that is valuable data for the robot, or valuable data for you as an engineering team to improve your robot, or even valuable data for the customer to see how they want to improve their warehousing system or whatever it is that they're doing. So I think of all the failures, yes, you can get information out, but then it makes it really hard to compare one failure rate to the other one if it's not particularly clear at what level you're talking about a failure. And I think for me, that's sort of the struggle that I see there, especially sort of in the struggle between like industry numbers and academic numbers and papers.
Mm-hmm. And I agree. I think we want to have kind of different levels of different kinds of failure or benchmarking evaluations, right? There's on the one hand side, you want to evaluate capabilities that seem totally basic and fundamental, meaning that they should be more or less as independent of the application as possible, because you want to test the broad applicability of something, which means something like, okay, can you pick up an object, right? An arbitrary object or something like that. Or the next one could be, can you place it in an arbitrary configuration? And can you move it without slipping and keep it firmly in the hand and things like that. And then there are metrics that are maybe more application and system driven, where you say, okay, like how many objects can you handle in an hour or something like that, that are more relevant to applications. And I think we want both, because the application driven ones, ultimately in robotics, they tell us what really works and what doesn't work, right? As we know, because it's all about complete systems that we have to look at, right? And just looking at the individual components can be good for certain research tasks and research directions, but overall we need to also look at the overall system. So I think both of these kind of levels are important to look at.
Actually, just on that note, and you see, we were very big on this mean picks per hour, right? And I thought that was the key metric. But I've learned actually something new fairly recently. And it's the following, that mean picks per hour is throughput, right? That seems to be very valuable. But there's another metric, which is when the system actually needs to be reset. And that means that it's there's something that basically causes it to stop altogether. Something goes wrong, it jams, or it overloads the arm or something. That turns out to be they really want to minimize that metric. So that's a mean time to failure, if you will. And interestingly, It is inversely proportional to mean picks per hour, because you can crank up the mean picks per hour, but as you do that, you're cutting corners and all these things, and that causes these catastrophic failures. And then so you kind of can't have both, right? So it's really interesting that if they just want mean picks per hour captured over a fairly short window, yeah, we can do that. But if you want this to run, 8-hour shifts without interruption, then you got to crank back your mean picks per hour to make that work. So it's really interesting. It wasn't obvious at all to me until recently.
Mhm.
So that's actually, I think for us, there's two metrics that we've seen that industry partners are interested in. One is this mean time to failure, which usually is like fully catastrophic failure that you're referring to. The second one is mean time between human intervention. And that's sort of the other one that is highly relevant, especially sort of in, as you say, like 24/7 or 8-hour shift operations where, if they say, well, if this happens every hour, we need to have somebody standing by anyway, so why are we paying the robot for? So that seems to be a very critical aspect of it. And yes, it's a question how that translates into metrics for an academic paper sometimes. I don't know if you have any good ideas there or for the researchers out there, but I think it ties back to the robustness aspect of the system, right? So the system metric and how we evaluate system performance in robotics papers, that's something that we can think about, right? Is it the one shot of the one video where it worked that we're going to report in the paper, or do we trial it like 5-6 different times? How do we report this, right? I think that's the other, for me, question as to the robotics community is like, what is sort of standards that we should agree on? Because obviously nobody wants to stand there for like 2-3 weeks before every paper deadline to have the robot run, right? And that seems a bit excessive, but also you don't want to just have like the one cherry-picked solution shot that just shows, hey, it worked this one time. So I don't know. Maybe I don't know if you have any ideas on how to approach that.
Just a note also with this mean time between interactions, right? There's different kinds of interactions, right? One would be person has to be physically in the space. Another one would be, okay, can someone remotely just briefly touch a screen and say that's what the robot should do, or things like that, right? It's really very tricky. Yeah, and I think the problem often is that for these longer term evaluation in the more complex manipulation tasks, that we just still don't have systems that have a robust enough base capability so that you can just run them for hours, right? It's still often, okay, you try your coolest new whatever grasp approach or something like that, and that's very special and it's for the first time ever running, and you just before the deadline try to get it to do enough grasp so that you have some statistic for your paper. Often kind of unfortunate that we are maybe not quite at the level yet to have systems that are robust enough. I can imagine in the top-down picking, I think we are closer, right, where you can actually run these things for hours and hours, hopefully, and do longer term evaluations.
I see that as actually a potential for industries and startups, right? I think parallel in self-driving cars and autonomous vehicles, right? So lots of people did, it drove around my office once or multiple times, but like nowadays there's like, thousands of kilometers out there, from companies that provide data sets from Google and Oxbotica, and that really allows you to test your things on long or on longer deployments on actual systems. And I think that's sort of really a push because, as a research lab, you sometimes don't have the resources to do that, right? But as a company, that becomes critical for your engineering efforts, because at some point you want this car to like drive, hundreds of thousands of miles out there. So you need to test it. So I think that's an interesting avenue to sort of foster more collaboration with, startups and industry. So for example, for us, we've definitely focused a lot more on our R&D efforts on long-term testing than it is on brand new, papers or metrics or developments, because in the end, the question is not so much can you convince the customer that your latest neural network performs to a certain number, but can your system perform up to the cost of intervention or up to the throughput or whatever other metric they're choosing, right? And for that, you do need testing and you need engineering efforts that are maybe not always totally included in your research papers. But I think it would be highly valuable to bring that back to researchers. And I don't know, Dieter, if you have any specific sort of things you can say about NVIDIA there and how that collaboration works, or there's sort of a joint effort to improve on that side between your UW and NVIDIA placement.
Yeah, I think on that, first of all, I totally agree that I think from the autonomous driving, one thing we can learn is really this notion of continuous testing, right? Developing, testing, going through the data, collecting data, labeling data, and that at just a massive scale, which is something in robotics we are absolutely not used to, right? And that's also because, of course, there's not quite the money behind it right now, right, in the use cases. With respect to NVIDIA, I think their one thing we're pushing is also using more simulation environments, right, for developing, training, and benchmarking manipulation systems. And I think as the simulators get better and better physically and photorealistically, yeah, more photorealistic, I think those capabilities get better and better. And also with these abilities to just read in all these different databases of different assets, right? That's another problem. Where do you get all the assets from so that you can manipulate the objects in these environments? But I think simulation can help quite a bit, but then also, of course, large scale, real world test sites, right? That could be really, really useful.
Yeah, I guess coming back to these metrics, I was thinking that it's a very good sign that the metric for grasping now is how many things you can pick every hour, right? Because, but if you go to more, say, multi-fingered manipulation, it's still so far away from even thinking of coming up with some sort of like unique metric. What do you think of? Because it seems to me that picking things from the top with the gripper, this is almost a solved problem, right? There's so many people. There's such a big push from e-commerce, this Amazon, this kind of thing that just want to pick things and put them in boxes, right? But then there's the whole other more academic side of it, which is, you know, maybe multi-fingered manipulating something using tools, which is so far behind. And this, I don't think people have even started thinking about metrics for that.
No.
At least not at the same, not you know, something per hour or whatever.
But I can't, I have to interject that. I just want to say that is not a solved problem in, you know, in Amazon and warehouse picking right now. It's not solved. I mean, I think you're absolutely right. There's a lot of groups working on this right now. And, you know, but remember, we had a lot of people working on self-driving cars too in urban settings. So it's not a guarantee we're going to nail it. And I think what we're saying is that this was what I've been learning, and you say you're learning this too, is like you know, because we have a startup that's actually building these systems, and it's so interesting to learn the nuances and complexity of what happens in, you know, what's really required in industry. So absolutely, you know, I think that there's not solved. There's a lot of interesting scientific research that needs to be done to push us further, to really get to the level of being able to make these practical and effective in industry. So you know, it's not as sexy maybe, but to me it is. I find those questions very interesting. Just really, really robustness over long periods and really getting those things to work in a cost-effective way. Very, very subtle and hard problems.
Yeah, I was just commenting that it's a good sign that it's now being measured in picks per hour, or you know, how many hours it can run. Like,
I think Joao made one good point, especially with respect to, if we talk about affordances or things like that, right? We do see papers where people work on affordances, but there's no agreed upon even way to think about affordances, right? Or how to evaluate it, or how you would benchmark it so that you can pick up objects for a specific task, and how often you would be able to do that and things like that. I think we are just, yeah, far away from that, from the basic capability, so that we can even do the kind of tests that we would want to do.
And I guess that sort of also ties back into the multi-fingered aspects of it, right? So the question is, where do you need multiple fingers for, right? And I guess that is both an academic but also an industry question. And industry is usually trying to keep it as simple as possible because you want to keep that robustness up. But I think that ties in with the, what do you want to do once you pick up an object? The grasping aspect is a tiny aspect of manipulation, right? And it's only a tiny aspect of the robotic systems that we want. We all want robots to go out there and, Wall-E type, go out and clean the world for us. But for that, grasping itself is a tiny aspect. It's the same aspect as like driving around. That's a tiny aspect. You need to integrate all these things together on a higher level to then make actually useful, things happen in the world. You need to usually drive somewhere, pick up something, and then you do something with the object, right? So the grasping solves the tiny aspect. And I think, yes, we're maybe getting to this point where we're robust enough to, use this block as something in a bigger building block. And maybe that is one way of calling it solved. I agree with Ken, it's not solved. And I think it's very interesting to see how you can actually robustify it and commercialize these aspects. There's a lot of research still going on that needs to be happening there. But it's also like, it's just a little block in a bigger picture. And for me, that's really the interesting aspect. And that's sort of where multi-fingered comes in, right? If you want to pick up an object and do something with it, that's really where the fingers come in, right? That's really where some of the smarts come in, so you can actually do something with it. And I agree, we don't have a metric for that. And maybe we don't need one metric to rule them all because we are so early on. But if you define a certain amount of tasks or certain things that you want to focus on, maybe it's handover or placement in a very, I think Dieter mentioned it, like placing it in a predefined 6D conv. That means that actually you have to pick it up and then usually do something with the hand and the object while you have it in there. And I think that's a really interesting aspect to try to maybe use a metric or at least a common goal or a common task description to push forward what you can do with multi-fingered hands. And I think that's sort of what happened I think the MPPH partly came out of Amazon's drive to do it in the Amazon challenges, because in the end got you the points. If you had more objects picked in the half an hour, 45 minutes that you got, that's sort of what won the competition. But it sort of trickled down into us understanding what is important for the system. I think if we define a task for like fingered systems and dexterous manipulation, and maybe it is the Rubik's Cube, I don't know, but like, how can we then trickle that down into metrics that we can report? I think that will help us push forward the state of where we are with multi-finger grasping.
Yeah, I mean, I'm glad you brought back the Rubik's Cube. Because I mean that was that's a very interesting example of in-hand manipulation, and I fully agree with everybody here that there's vast amounts of unsolved problems, and I just wanted to say that just even at the bottom, what seems to be obvious and simple is also unsolved. But let's talk about the failure modes in that story. I think it's really interesting the way that was received by the press and by the public, that that it is this manipulation. But when you look much more closely, it was very, very I would say limited result, and it seemed to say something about curriculum learning and something about domain randomization. That was interesting, but it wasn't a breakthrough in the sense that it didn't really change radically, I think, the way we do manipulation, multi-finger manipulation. I'm curious how others feel, because that was a case where they also tended to not talk about the failure modes too much, right? They showed the beautiful video, and then it was also because it was Rubik's Cube, people got very confused about what was actually being done there. So I don't know. I mean, I think that's interesting to talk about in the context of failure modes, that story itself, because I think it was a good lesson for us, just to be careful about how things are presented.
Yeah, I agree. I would also like sometimes to see some more of the details, especially with this, when people say, for example, also some of the earlier work on domain randomization, right? When you say it was solidly trained in simulation and it immediately worked on the real system, what people typically don't tell you is how many months or maybe years they spent on trying to find the right domain randomization parameters such that when they randomize over them, it finally works, right? Through how many iterations they went in this process. And typically that's not really being mentioned, right? And that would also be interesting to see kind of these kind of failure modes, right? Where you domain randomize and you ignored some aspect or so, and your robot did some crazy stuff because of that.
Absolutely. So I think domain randomization is so important because it actually is a way of addressing this sim to real gap. You know, we did that. We did stochastic, you know, optimization around all these parameters like center of mass, friction, pose, error. But we were really interested, and this is actually a project that's been a little bit on hold, but with NVIDIA, and Dieter, you know a little bit about this this project, but it's really, I think the idea of using simulation to simulate, let's say, thousands of slightly randomized versions of the same command, but with slightly different conditions is really interesting. And as you said, simulation can help you do that in a much more sophisticated way. And if you can, but that requires a lot of speed and computation to be able to run those. And I do think there's something there. I think that's really interesting.
Yeah. Well, in one line of work we're doing with the space sim, for example, is then how can we use, if you do some real world experiments, how can you use these to refine your domain randomization, right? So that you're not bound to do like crazy randomization over everything, right? But maybe a bit more focused randomization.
Yes, that's really interesting. So learning and feeding back so that the domain randomization gets tuned appropriately, that's really interesting. Mm-hmm.
Yeah, so I was thinking maybe we could have so we have five people who submitted posters. Some of the presentations, so we went through them. Some of the presentations are sort of relevant. Some of the things you were talking here. I was wondering maybe it's 10 past. Let's take about half an hour, hopefully, to go through them. And then that leaves us another 10 minutes in the end just for some final considerations. Is that okay? Or is there something is there any other question you would like to raise? Any other?
I think there was one on uncertainty in the chat.
Oh, that's right. What do you think of the role of uncertainty? The role of uncertainty could play in grasping from either end-to-end learning-based methods and methods with interpretable intermediate steps, object geometry, for example. So the role of an uncertainty in learning-based methods.
So I think it was sort of mentioned, maybe not explicitly, but it came up a few times before. And I think personally for me, uncertainty is important, right? And I think there's two aspects to it. There's the can we model the uncertainty of what is going to happen, and sort of like how do we deal with things that we didn't expect, and can we expand our trained models or even handcrafted model to deal with a broader range of what can happen. But I think the other part for me that's interesting is if we're using models and, for example, a grasping model, and we want to use that in a broader task, like a manipulation task, a handover task, whatever it is, how can we get an uncertainty out of this model, either if it's a neural network or not, doesn't really matter. But that allows us to make that choice of what system to use at what time, or how much to trust a sensor over another sensor, right? So, and I think that is for me a quite interesting aspect from a systems design point of view. And yes, maybe you can at some point enter and learn everything, but that's probably not where we are at this stage. And when you want to combine it with like existing models out there, what is a good way of feeding that uncertainty through, or at least providing some level of uncertainty? So I think it's important.
I think it's just a part of this whole reasoning system that you need to, to analyze failures and to come up with alternatives, right? Thinking about why things went wrong and what kind of uncertainties might have been involved in that. Yeah.
There's a slide, one of the slides will be precisely about the uncertainty on the pose of the object. Okay, so can we move on to this small presentation? So what I'll do is I collected the slides, so not to be sharing passing on the sharing the screen. I'll be sharing my screen and just unmuting the person who's the author, and then it just if you're the author, just try to be briefly describe what your work is. Okay, so the first one is Xingao Zhu from Berkeley. Let's see if is in. So I'm gonna unmute you, Xingao, and
Hello.
yeah, hi, and I'm gonna share my screen.
Okay.
Is it okay if I share it like this?
Yeah, it's fine for me.
It's fine. It's not going to presentation mode.
Okay, so I guess I can start
It would be
now,
nicer
right?
actually, if you could, if there's no reason not to go.
Say again, but I don't know. Does,
A slideshow
Yes.
mode, right?
yeah, does that did that make any change?
Yeah,
Did
works better.
works better now.
Okay.
Okay.
Okay, so I'm Xinghao from UC Berkeley, and today I would like to share you guys some observations about the multi-fingered grasp in a cluttered scene. So in our previous work, we proposed a grasp pose detection GPD-like algorithm for multi-fingered hand, which the pipeline is shown top figure. So the algorithm basically achieved about 72 single object grasp success rate and 60% object removal completion rate in cluttered scenes. However, we observed two failure modes, which are common in multi-finger grasping tasks and are rarely introduced in parallel finger grasp. The first thing is the GPD framework performs poorly in narrow spaces. On the one hand, it tends to produce grasps that collide with the ground or flat and small objects. And on the other hand, in cluttered scenes, many grasp candidates were pruned due to the collisions between the gripper and the surrounding objects. To solve these, we found that performing a sample space pre-filtering by some predefined heuristic can be quite helpful. And then the key here is that we would like to reduce the computation time complexity. And besides, we found another thing quite useful is adding additional local grasp optimizer, which can efficiently handle collision problem by probably formulate things as a tree job. And second, we observed that the gripper may slip on object surfaces if the planned grasp are executed by some simple grasp policy. The slippage basically comes from two things. The first is the missing of reliable collision detector. And also the second thing is the contact force controller. So for first kinds of thing, without a precise and complete point cloud of contact detection, different fingers may have asynchronized contacts with the object in a pre-contact phase. And as a result, objects may shift before forces are applied. And in the post-contact phase, the gripper may apply non-internal forces to the object, which causes net objects improvements. And intrinsically in parallel gripper, this kind of object slippery is not heavily studied, since parallel finger intrinsically alleviated those problems in the sense that object movement is restricted in the gripper's open range, and also applied forces are always antipodal, which are intrinsically balanced. And these two observations suggest that probably developing a contact detector and a post-grasp controller can help to reduce the object slippery, and which I think is quite similar to what Juxi has just mentioned, that for multi-finger hand, we are planning to introduce some manipulation consideration in the grasping phase, which we build a new matrix to see whether a grasp is able to improve the manipulation task after the grasping. And hopefully this work can catch up the coming deadline. And well, if you are interested, just you can ask about the details later. And that is what I want to share about failure cases for multi-finger grippers.
Thank you so much, Xing Hao.
Thank
Very
you.
much. If anyone has questions about these slides, just write them on the chat. So your slide, I guess, kind of touches a bit on this thing that also was mentioned about how the how the context may change the pose of the objects ever so slightly, that it now makes the grasp fail, right?
Yeah.
That's a big issue, I guess.
Yeah, and I think the good thing is, actually, I think what I mentioned here is actually what just professors discussed. So probably a tactile to detect object slippage or some vision sensors can help. But yeah, that is on our future works.
Okay, absolutely.
You raise a great point. I mean, when we were talking about sensing, we were talking about the hand obscuring or occluding the camera, but you're absolutely right. This is another great case where you have other objects occluding the camera. Xing Hao, and that is a really fundamental challenge. Is essentially we are trying to extract a single object here, and this is what we call mechanical search. You're trying to find an object and get it out of a cluttered scene, and that's a really nuanced problem, and somewhat different than just picking up picking up the first thing on the top of a heap. So I feel your pain. It's a hard problem.
Yeah, but actually one thing I want to say is that during the execution, I realized how good, well, probably the previous works are. For example, the DexNet and also the 6 degree of freedom GraphNet by Professor Fox, and also, well, the previous works from Amazon Pickup, like Jux's work and all of your guys' work. So yeah, well, for sure, grasping things in a heap and probably decide the sequence of grasp is quite important. And in this work, what we did is really just basically see whether this object is able to pick, and then we pick it without any probably a heuristic sequence. You see whether we have to pick this first or to determine a really reasonable sequence. So yeah.
And just one quick point. This is also an example. I think I'm sure you've seen in your own work. Wouldn't it be nice if there was now, let's say, a benchmark environment or data set, even if it's simulated or so, where you could really just test your system and then analyze it and compare it directly to all these other techniques, right? So that there is some kind of clear measure of how well it does, and you could analyze kind of the specific failure cases and things like that, right? We're still often in the business of these one-off results, right? And everybody does that because there's just no clear benchmarking system out there for that.
Absolutely.
Yeah.
Absolutely.
Yeah.
And you make a video and you submit the paper and
yeah.
Okay. Let's move on, just in the interest of time. The next speaker is Lima Agnel Tony from the Indian Institute of Science. And I think it brings us a subject that we don't think about very often, which is aerial, there's aerial aerial grasping, right? Lima?
Hello, can you hear me?
Sure, yeah.
Thank you for accepting our work. I am Lima Agnel Tony. I'm a PhD student from Indian Institute of Science, Bangalore. So this work is done by a group as a part of competing in a competition, which is called Mohammed bin Zayed International Robotics Challenge. So likewise, how mentioned, the grasping, what we had been discussing so far in this workshop, and what I am going to present are, quite likes on poll. But I hope this will inculcate some interest and appreciate the challenges that we are facing in this field. So the problem is aerial grasping. The statement is like this: we would like to aerially, autonomously use the manipulation to grab a moving ball. So we have a target drone, which will be having a ball which is hung below it. And the objective is to track it, detect, track, and grab the ball and get back. So it is aerial manipulation, or in other words, aerial grasping. So the proposed solution for this problem is like we can see in the slide, the left corner picture if you see. So it is a single degree of freedom manipulator, and it has a basket kind of end effector. So why single degree of freedom manipulator? Because everything is moving here. The challenges that we have in this grasping is way different from grasping something which is static. So if we are having multiple degrees of freedom, computing the inverse kinematics, the delays associated, and the related complexities, which will complexify the entire situation. That is one thing. And the second thing, the reason for having a passive basket kind of end effector. When it comes to aerial vehicles, endurance or the flight time of the vehicle is quite important. So that directly depends on the power consumption of the sub modules which are on the system. So we really want to minimize or optimize the actuations or the power consuming units within the system. So having a passive element or a passive end effector helps. And besides, if you're having a finger kind of system, the timing that is required to have a successful grasping is also quite relevant, given that the target is also moving. So in that way, the passive nature of the end effector helps. So while having field experiments, we had a lot of experience and a lot of failures, and we learned a lot from these failures, a couple of which are mentioned in the slide.
Okay.
So, sorry, I think the
Sorry, I
slide changed.
clicked by accident.
Okay. So
Fair
the
to say.
first reason is the improper size of the end effector. So the organizers themselves had given a size constraint on the entire robot plus manipulator system. So given the dimensional constraint, there is a limit to which we can increase the size of the manipulator. So of course we could put the manipulator to the center of the drone, but any collisions will be lethal to the system itself. So we cannot afford to have a manipulator on the body. So we have kept it to the side. So there are stability issues because of which we cannot have a manipulator that big. So that was one reason of the failure. So what we could learn from the consecutive failures and experimentations is that it is always a trade-off. Given a system, we cannot have very big manipulators, but at the same time, we can find an optimal point, a sweet spot at which we could find a balance. The second reason is inefficient grabbing algorithm. So when it comes to grabbing algorithms, it has to be robust. The reason is that because the drone which is carrying the ball itself is moving in a particular speed, and it is in an outdoor environment where it is subjected to various disturbances like wind, the object that is to be grabbed is having a constant motion, and that too very much random. So we used an image-based grasping algorithm initially, but we found out that any noise in the pixels and the feedback associated with that led to greater errors. And later we had to integrate prediction and estimation and a guidance-based grabbing methodology so that successful grabbing could take off. So from that scenario, the failures were great lessons on how we could improve the algorithm as such. One another interesting reason is the agility requirement to the terminal phase. So what I mean by the agility requirement is when the basket is so near to the ball, due to the before mentioned reasons, the ball could always move. So as a result, the drone also should position itself quite in a very quick manner so that the successful grabbing happens. But we know that every dynamical system, there is a response time associated with it, because of which the system cannot really respond that quickly. So the requirement of quick agile motions towards the end of the maneuvers were also a contributing reason towards the failure of grabbing. A solution that we could design through experiments is to correctly course way early so that, and also try to grab when in the motion is slightly better, meaning the drone carrying the ball is moving in a linear fashion and not having any quick turns and twists. Then another one interesting reason is the vision. So as I have mentioned, this is completely a vision-based pipeline. So likewise, the finger grasping mechanisms that we have discussed. Here also, the manipulator has an eye-in-hand configuration. A camera is fixed to the center of the basket so that visual feedback is used for grabbing. So unlike the scenarios in which we do grabbing in indoor environments, the scenario outdoors is starkly different. The lighting changes in the course of time. Then here, for example, the ball is spherical and red in color. So any similar colored red distracts would give away the vision. So the accuracy with which we could detect something outside and inside are way different. So the challenges also are very high. And one other reason could be the sunlight glare. Then the camera calibration is also very much important in this regard, which plays a big role in failures. So vision plays a big role, and we found out so many reasons for failure, which because of which we could fix the thing. And last but not least, computational delays. It's a obvious thing that happens in any physical system, the delays. So generally, what we could observe is that the vision modules often, slow down the entire process, because of which the drone reacts to the system a little bit late than it is required, and the failure happens. So several optimization algorithms were also, introduced so that we could make the things better. So these were some of the failure reasons which we found out and which we addressed so as to have good grabbing. And these failures were great experiences for us in understanding the challenges involved in aerial grabbing. Thank you, and I'm open to questions.
Yeah, thank you. I don't think there's going to be time for I'm sorry. I mean, if there's a quick question from someone, this is of course it's a very different domain. Like you have all sorts of issues that people using arms and hands don't have. Like, for example, this last one. So because you do the computation on board, right? You do the computation on the drone. It's not like you're not sending to. So there's all sorts of limitations that we don't usually.
Exactly. The challenges that we have in hand for aerial manipulation is way different from a robotic manipulation. We have to optimize everything to get things working.
Very much.
It's a pretty amazing system, by the way. Awesome.
Okay, so next, thank you very much, Lima. Next presenter is Neil Doshi from MIT. Neil, let me try to find you. There you are. So Neil is going to present a poster about tipping an object, right?
Yep. So this is like a pretty simple example here where we're trying to pivot an object whose mass distribution, center of mass, size, etc. are unknown about an environmental point contact. And so here, to simplify it, we assume that the robot makes a sticking sort of line contact with the object, and the environmental contact is a sticking point contact. And so we do assume the coefficients of frictions are known. And basically, just using force sensing on the robot and its proprioception, so just knowledge of where the end effector is in the world, we try to estimate the inertial mass and sort of geometric properties of the object, and then write the object to get about some desired angle while maintaining sticking contact. And the approach I think it's pretty straightforward. We're just using an extended Kalman filter to estimate both the state and system parameters. And then we sort of linearize about the most recent system and state estimate, and we do linear MPC to satisfy linearized versions of the kinematic and force constraints. And this is pretty preliminary work, but the overall idea here is that when you're doing this type of non-prehensile manipulation, you have these external environmental contacts, and a very important or a failure mode that comes up a lot is that you can't enforce the mode sequence that you planned when you're doing model-based manipulation. And so the idea here is some type of online adaptation that both better estimates the parameters of the object, and eventually, considers different like sticking and sliding different hybrid modes, so you can also estimate the friction at this environmental contact in order to enforce the mode that you've planned. And the hope is to do it through trying to use as minimal sensing as possible. So right now we're just using proprioception and force sensing. Maybe gel sight is an option, and we could always use vision if we have to.
Okay, and just by tipping, like what are you estimating? Estimating the mass of it, the friction, like Coulomb friction.
So we're not estimating the friction, we're estimating the mass. Where the contact is, we don't know. Where the center of mass is, we don't know. So those things you can estimate just by sort of tipping the object.
But when you say inertial, you don't mean
Like the moment of inertia?
the moment of inertia.
Yes.
Okay.
I mean, so you can't estimate these parameters exactly. You can estimate ratios, but they're sufficient for control purposes. Like we're not trying to exactly system ID the system. We're just trying to learn the parameters that enable control.
Okay.
So my comment is that I think that you are tracking a very difficult problem. So can you expect how many parameters can you identify, or is there any parameters which cannot be identified?
Yeah, so like for example, there's certain, you can't do mass, oh I forget, it's mass over length or inertia over length. You can't identify those uniquely. So you have to assume that like the length scale is 1, and then you can identify the ratio of these parameters. And right now we're not identifying the coefficient of frictions, because if we assume everything is sticking, then you basically are always in the interior of the friction cone. So you never get to actually to the boundary where you can identify where its slip begins. But I think eventually we'd want the estimator to have maybe sort of different beliefs for different hybrid modes at the environmental contact, like sticking versus slipping versus sliding. And then you can sort of use that sort of like a more hybrid type of estimator in order to deal with that kind of friction estimation.
Thank you.
All right, thank you very much, Neil.
No problem.
Next presentation is also from MIT. Collaboration with Amazon Robotics. Karis Moses is presenting. There you are. Okay.
Hello, can you hear me okay?
Yes.
Awesome. Hi, everyone. My name is Karis. I'm a student at MIT. And yeah, I'll be talking about work I did over the summer with Amazon Robotics. So in this work, I focused on a segmentation-based approach to picking. So the method I was starting with is shown in green. And so the robot receives RGB and depth data, and the RGB image is segmented, and those are used to segment the point cloud. And then within these proposed point cloud segments, pick points are determined based on kind of engineered heuristics, such as searching for flat surfaces in the point cloud that would result in good section. Then these pick points are ranked based on some more engineered metrics, such as the confidence in the segmentation or the flatness of the picking region, things like that. And this goes into a ranked pick point list, and the robot just starts picking from the top. And so while this was achieving really good performance, there were still failures that occurred. And many of these were caused when the segmentation process produced erroneous segments. And so while deep learning methods excel at generalizing, they're still prone to errors, as many have already noted today. But if we aim to make these systems 100% robust, then we need ways of predicting these errors rather than relying on these methods to improve with more training data. So I focused on segmentation and clutter specifically, and some of the errors, these errors occur due to the huge state space that the model's expected to make predictions over. So the ways that objects fall in relation to each other is very complex, and the context states that are created are very high dimensional. So some of the errors we were seeing were if objects fall in a way that kind of create a plane together, they can often be segmented as one object. And then the robot might try to section in the middle of this and not get a good graph and drop one. Another common error is if an object is very textured, it can be over-segmented into multiple objects. And then it might think it's picking up an object, but it's really picking up kind of close to the edge of a larger object. And then it will fall due to the torque at the section point. So in this work, we aim to predict errors in segmentation by incorporating some state estimation. And we assume that we roughly know the bounding box dimensions of the objects that the robot is expected to interact with. So our proposed method is shown in the larger blue box. So specifically, we aim to estimate this bounding box using a particle filter. So once we have the segmented point cloud, we fit a bounding box to it. This serves as the observation. We update the, calculate the posterior, and we use the known rough object dimensions to calculate the likelihood that these observations belong to a true object in the scene. And then we predict the erroneous segments with some likelihood threshold. So if the likelihood that a segment belonged to an object is very low, then it was probably an erroneous segment, meaning it either grouped too many objects together or over segmented an object. And if the observation falls into the distribution of things we know to be in the scene, then we say it's okay. And then these kind of likelihoods or error predictions could then influence pick point ranking, just to be kind of another metric to resort that list. So with this method, I was able to predict 89% of the erroneous segments that the network was presented with, or that the network produced. And these are preliminary results, but I think they're very promising and show that while full state estimation may be too inefficient, local fast approximations of the scene state might be enough to improve pick point selection. Thank you.
Karis, can I ask you a question?
Yes, I don't know where that's coming from, but sure.
Ken Goldberg, sorry.
Oh, yeah.
Interesting work. So I'm curious because segmentation is definitely hard in these kind of scenes. Now, I'm trying to understand the, you're saying to detect erroneous segments. So you have ground truth, I presume, right? And is the idea that you're, the method is able to then, I mean, what is the basis for it to be able to say that the segment is erroneous? Is it because
So
of noise or uncertainty?
Is it because what? Sorry, I didn't catch that.
I'm just curious if it's noise or uncertainty. I mean, I really like this problem. I'm just trying to understand a little better how about it.
So I don't have ground truth. The only information we have are the kind of bounding box dimensions of the true object. So imagine that you already have this segmentation network trained. Then you're presented with some novel objects, and we don't want to have full detailed models of these objects, but we might just have a rough bounding box. Like this thing is 10 by 10 by 10. And then so when we put the scene through the segmentation network, some of the things that it segments might be grouping more than one object together. And so basically I'm just saying if these observations are outside of the known dimensions in the scene, then it might be an erroneous segmentation. Does that make sense?
Yes. Okay, I see.
Okay.
So you can do a check to see that it's consistent with the size of the objects that you're expecting.
Yeah.
Okay.
Yeah, it initially started off with obviously like loftier goals. So we kind of wanted to see if more rigorous state estimation could improve picking. Like you still want to leverage the generality of these learning methods, but we need some way. That's kind of why I asked my question earlier. We need some way of calculating kind of how confident we are in what these networks produce. And so one way could be to try to get a more accurate, like use them as observations and try to get more accurate information on what the robot is actually interacting with. Right.
Okay, good. And then I'm just curious if the next step would be once you detect an error that you want to correct it by, in that case, what? Sort of then conjecturing different segments that would explain alternative segmentation there?
Yeah, that could definitely be one way, kind of a reactive strategy that says maybe if the segment is too big, then kind of like poke around to try to move the objects into an easier configuration. But another thing I was saying that might be easier is just kind of downweight the points that fall into those segments because those might result in failures when you actually try to pick it up. So only try to pick the objects that have like confident segmentations.
Okay, good. And you work with Tomas and Leslie?
I do, yeah. This was Amazon Robotics work, but I'm in their lab, yeah.
Okay, cool. Thank you.
Quick question from me too. Very interesting work, Karis. We're also looking at segmentation and topics like that. And one question, do you imagine it would be possible rather than taking, let's say, the segmentation network and then just taking its output and then combining it with an explicit state estimator to kind of incorporate that into a joint kind of end-to-end system, so that you could almost imagine you end up with an iterative segmentation algorithm that internally reasons about how certain segmentations might fit the object dimensions, and you put this kind of inside the network reasoning itself.
Mm-hmm. Yeah, I think that would be really interesting. So kind of maybe like feeding back my error predictions into the network.
Exactly.
And taking that as kind of another input.
Yeah.
Yeah,
And
no, I think that would be a really interesting idea.
Into the network, right? Let's say you could, the input to the network could also be that, okay, these are the object dimensions that we're expecting to see. And the network could take those as input and maybe improve the segmentation directly through that.
Yeah, I think that would be really interesting. That's a good idea.
Thank you.
Thank you.
Yeah. Okay. Thank you very much, Karis.
Yep.
Let's go to the last one. That's Anjali, I guess. Anjali is from Oregon State University.
Hello. Hi, can you all hear me?
Yes. I'm sorry if I mispronounced your name.
No, that's fine. I'm sorry I didn't add it to the slide. I realize it should have probably have more information than it does right now. Fill that in with my explanation. Hello, everyone. I'm Anjali Asar. I am a master's student at Oregon State University. I work with Dr. Grimm, Dr. Cindy Grimm. And I'll talk a little bit about how we're adding structured noise for more reliable grasping. So it goes without saying that there is no such thing as a perfect grasp. There's always going to be noise in the sensor. There's always going to be environmental constraints such that the object pose is not what the robot hand expects it to be. And we found that it is, we found it important that in order to build a robust controller, it is not only necessary to include different types of grasps, but also these deviations from expected poses of the object. So one might argue that you could just generate these random poses on the fly, but we found it more beneficial to have a predetermined set of poses that we save and then reuse. Having these fixed yet random data, it allows us to compare different algorithms against the same data set and giving us insight into what type of noise that these algorithms can handle. And also, if we have a mechanism to label these poses based on the success rate of a baseline algorithm, we can divide the set into training and testing data with a more equal representation based on the success rate. So what we did for our work is we sampled a graspable region within the robot hand span, and we generated noise by adding rotations to the hand relative to the object, like plus or minus 5 degrees, and we moved the object within this graspable region. We did this for 3 different hand grasp orientations, which we thought were quite common. One, you can imagine, so the one we've showed here is what we call the side grasp viewed from the top. And then there's also the top-down grasp, and the third one we call the tilted grasp. You can imagine these as 3 grasps along the X, Y, and Z axis. So after we then filtered out some starting poses that ended up in collisions with the hand, and we generated a data set of 5,000 valid starting coordinates of this object. For our work, we classified these poses based on the success rate of a naive controller. And we defined a naive controller as one that simply closes all its fingers at a constant rate. And these are the results that you see on the slide. So the insight we get from this data set is that, so the object we used here was a cube. And the insight we got from this data set was that this cube poses closer to the center of the palm and towards the edge of the fingers tend to fail for this naive controller. And for our work in the future, we are interested to train a reinforcement learning algorithm to intelligently close in on this object using this data set. So this clean data set provides us with a more uniform testing and training data, and also helps us evaluate how our algorithm performs against this naive controller. And over time, with more evaluations versus different algorithms, with more grasp poses also, it can give us more insight into which one of these poses end up being more challenging versus less. And it can also give us also help us while transitioning from simulation to real world as well. Thank you.
Thank you, Anjali. So this kind of goes with some of what was discussed before about uncertainty and noise on the sensing, right? But how do you decide on the level of uncertainty?
Hi, sorry, I muted myself. Would you mind repeating the question?
So how do you decide on the level of this uncertainty, of this noise?
Right now we just sort of a trial and error, plus or minus 5 degrees above the hand, and we're trying to keep the graspable area within the hand span, because we're interested in grasping an object which is in this vicinity.
So I'm guessing. I'm sorry.
Sorry, yeah, only based on future work, yeah.
I'm guessing that, for example, if you're using one of the old Kinects, for example, depending if you're inside on like the ambient light, you might, your uncertainty scale might change.
Sorry.
So I mean, depending on the environment, depending on the hardware that you get, these uncertainties might change a lot, right?
Yeah, that's true. That's why we're saying that this data set is quite specific to what the kind of work we're doing. But I think what we want to put out there is this idea of trying to use a repeatable data set for your work.
Mm-hmm. Great. Okay. Thank you very much.
Thank you.
And I guess that does it for the posters. All that's left is some concluding remarks. Maybe Professor Arad, do you want to say some? Do you want to say some bring this all together and say?
Yeah, and actually, I was invited as organizer, but main work was being done by Joao and Dimitros, and I think that I really appreciate for organizing such a great workshop. And through this workshop, I recognized that this is a very, very important problem, and which has to be solved in the future research. And I think that this workshop motivated me to work on the problem of error recovery more deeper and deeper. Okay, thank you very much.
Thank you, Professor. Yeah, I guess I also want to just thank speakers, Professor Goldberg, Professor Fox, Druxy that left, Jeanette who couldn't make it, also the people who submitted contributions today, and also the people who attended. Thank you very much to all of you. I'm very happy with how this went. I think we had very productive discussions.
Yeah,
Ideas floating around.
I want to say, I think you really chose a great topic. I think it was really insightful, and I appreciate, because I think that failures, are so important, but nobody likes to talk about them.
Yeah, I know.
But you found that it's a really rich topic, and it's been really interesting, and I hope that you and Kensuke and others continue to do this, because I think it's an ongoing topic that we're going to learn from, and it's absolutely, this discussion is very inspiring. I would really like to I hope we can do this again in a couple of years.
Thank you. Yeah, absolutely.
I'd
I
like to
absolutely agree with you.
For this,
Yeah.
I think it's a really interesting topic, and it also, in my case, like preparing, for example, the presentation made me think about much more explicitly about these manipulation failures that we typically see, right? And typically, when you then look for videos, you often have many more videos of the successes than the failures, right? And I think it also teaches we need to document more about the kind of failures that we're making, and also putting them, I think, more explicitly into the papers. And I think this is clearly a topic that we would keep on discussing about.
Absolutely. I mean, this is not just, I think, a problem in robotics. This is science in general, right? Papers in general, whether academia works. I think in most fields, people don't really report their failures. Anyway, I think, yeah, I agree also with that this was a great topic. I can say that because it wasn't my ideas. It was Dimitri who, like, we were hanging out and he told me, you know what, you should do a workshop on failures. And I'm like, yeah, that's a very good idea. So it was all his idea. Okay, we're within the 2 hours. Thank you very much. I'm gonna stop the recording, and yeah, hope seeing you around.
Thank you.
Hope they come.
Bye.
Hope they come back with the normal conferences instead of these virtual. Thank you for staying up late as well. Thank you very much.
No problem. That's right. It's
Thank
midnight.
you. Bye.
Very
Bye.
much.
Bye.